Welcome everybody to the next 33rd mathematical colloquium in our School of Mathematics. And today we have a special guest, is Cristiana de Filippis from the University of Parma. And she was the European Mathematical Awards of Prize of European Mathematical Society. So welcome and please.
So many thanks for the invitation, and I'm very glad that all of you are here. This is a very prestigious colloquium, so I'm honored to be here. Today I will try to say something about the crucial role that regularity theory had since the very first steps of the calculus of variation. Okay. Is crucial information whenever you want to deal with the minimizers of variational integrals or solutions to equations, and in particular, it was at the core of famous Hilbert 19 problem. That was the following: you have a variational integral of this type. Let's consider its complete form with ingredients. Well, you know that it is elliptic in the sense of the behavior of the action and of successive derivatives. Moreover, you have analyticity with respect to all the entries. Okay. Now, crucial question. What can we say about possible analyticity of solutions? So this was the focus of one of the problems that Hilbert determined as central in mathematics of the 20th century. Okay, one of the most influential problems. And at least three of them were focused on questions related to the matter of regularity in the calculus of variations, boundary regularity, as well as development of general, more advanced methods in the calculus of variations. So this is particularly important. Now, what was known so far? So I have to just how to and doesn't work. No problem.
Should I try that now?
Yes. Okay. Now it works. Thank you. Now, related issue to this matter is systems, and just to highlight the catch between the variational integral I showed you before and general equations in this form. Well, you take as A as the derivative in the gradient variable of the integrand f, and as B the derivative in the u variable of B. Okay, so you're essentially giving answers concerning regularity to both minimizers of variational integrals as well as for equations and systems. Okay, what were the very first answers to this problem? Well, in 1940 in 2 dimensions, and I mean, having a priori that regularity are that the solutions are C3 regular is quite a heavy assumption. On this, there were several other crucial contributions by Hopf, Schauder, Cacciopoli, Morri, Relay, Nečas, and Radon, Petrovsky that eventually culminated in the following statement: if I have a C1 regular solution, then I can prove analyticity. So there was a non-trivial gap to be filled. Okay, that is the step from W12 solutions to C1. Why I'm saying W12? Well, I'm saying W12 because by direct methods in the calculus of variation, it is possible to prove the existence of solutions only in W12. So in principle, you cannot directly prove existence of C1 regular solutions. So you just get moving from W12 solutions to C1. And then, of course, if your program allows, you jump to analytics. Okay? Now, the very first and crucial contribution towards the solution of 19 Hilbert problem is the George theory that say, okay, whenever I have a W12 regular solution to linear equation with measurable coefficients that are elliptic and bounded, I can prove that U is locally Elder continuous up to a certain exponent that depends on the ellipticity ratio of your equation, that is now is the ratio between L and U. Okay. Now, this is this was first stated for this class of linear equation, but it is intrinsically non-linear in nature. And you will see in a while why this is true and why this result opened the way to prove regularity for a very large class of equations and variational integrals. Here we have a very young De Giorgi Nash. That's four. Okay, now one could say, yes, but why? You say it starts from W12. I prove that that minimizers or solutions are Elder continuous. Yes, but we say that the gap is C1, is W12 C1. So there is an enormous piece of internal that still needs to be filled. Carefully. This is the real power of the Georgi's iteration, the Georgian method. For simplicity, let's look at an autonomous functional that is elliptic and satisfies all the smoothness requirement needed. By minimality, we know that minimizers solve a PD, an elliptic PD, that is the Euler-Lagrange equation. Now, what I can do? I can further differentiate this equation in such a way that any component of the gradient, any partial derivative, solves an equation that looks pretty similar, no, to the one that essentially opened this talk, where now the coefficient is nothing but the Hessian of f evaluated on the gradient. This way, iteration applies. One can prove boundedness and afterwards continuity of the gradient. Therefore, the gap W12 C1 is filled, and of course, if your integral allows, you can push it directly to you can push it to analyticity. Okay. Now, from this, this was the first block of the domino stuff. Then, essentially, Moser found alternative proofs to this. Then there were seminal contributions by Madde, Stampacchia, Ladichenskaya, and Duraltseva, Bombieri, Giusti, Serrin, Trudinger, Landes, Nečas, Serrin, Leon, Simon, that in particular focused on the nonlinear case, on nonlinear possibly degenerate equations. Many of them were concerned with possibly degenerate uniformly elliptic equations that one can state in this general form. Okay. However, also the non-uniformly elliptic setting was intensively studied, starting from the 60s, with strong emphasis. Okay. Now, I said uniform ellipticity and non-uniform ellipticity. What am I talking about? Well, the ellipticity ratio related to an equation of a functional is defined as the ratio. I mean, if we keep in mind for simplicity, this nonlinear field here. The related ellipticity ratio is nothing but the highest eigenvalue of the derivative of A in the gradient variable over the lowest eigenvalue of the derivative of A in the gradient variable. Now, this is well defined by ellipticity. Okay, and what should be highlighted is that if this object is uniformly bounded, then we are dealing with uniformly elliptic equations. Okay, while if this object blows up on large values of the gradient variable, then the equation is non-uniformly elliptic. Let me highlight 1 second that the case of uniformly elliptic embraces all, let's say, most of the models one in general meets when studying the Laplacian is beautifully uniformly elliptic. The P Laplacian is uniformly elliptic as well. Indeed, although it may be the generator singular, the P Laplacian, this has nothing to do with it being uniformly elliptic. Indeed, in the case of the P Laplacian, the eigenvalues behave as up to constants. Of course, modulus of z to p minus 2. Therefore, whenever you find the ratio, you are essentially comparing two quantities that grow like modulus of z to p minus 2. Therefore, the P Laplacian is uniformly elliptic and the generator singular, depending on P larger, on whether P is larger than 2 or less than 2. Okay? While the non-uniformly elliptic setting is a totally different world. Okay? And embraces a very, very large class of families, as we will see in a while. Okay, now how we bring this concept to the variational setting, so to functionals? Well, this can be easily adapted by observing, by passing through the Euler-Lagrange equation. In case of functionals, by minimality, A is just the z of L, right? Just observe that the nonlinear tensor A becomes the derivative in the gradient variable of the integral. Therefore, the conditions on the derivative in the gradient variable of A simply moves to the action of F. Okay? And so we can recover the full definition of ellipticity ratios and all its consequences concerning its boundedness or its unboundedness. Okay, examples of non-uniform elliptic problems. Well, probably the most celebrated one is the area integral. It is pretty much non-uniformly elliptic with a very strong rate of non-uniformity. Its ellipticity ratio blows up the square power of the gradient variable. One can also consider a generalization of the area integral by considering very, let's say, degenerate infinity problems like this one for P larger than 1. One can consider models that approach linear growth. It can be taken as close as light to linear growth, but still maintaining a little bit of distance from B for having linear growth. One would also consider iterated logarithms, so approaching as much as possible linear growth. And then another example is that of isotropic energies, okay, or exponentials, if you like. Another example of non-uniform elliptic problems are exponentials, mediational integrals of this form. So let's say that this class of problems embrace the full growth range you could think about, from linear growth to exponential. So it is very generative. Now, let's turn back to the P Laplacian. Now, those are examples of degenerate singular equations, and there the theory is extremely delicate because now a very strong nonlinearity does no longer appear on possible right-hand sides. Now the nonlinearity is in the operator, right? And this makes the whole theory very delicate. What was proven in the scalar case by Uraltseva and in the vectorial one by Uhlenbeck, that energy solutions of the P Laplace equation have locally at the continuum gradient an exponent that depends only on the dimensions n on P. And this is significant because both under the scalar and the vectorial perspective. But what should be observed is that solutions to this problem are minimizers of the P-Dirichlet energy. Okay, can be recasted in a variation, of course. And okay, those were strong and significant contributions that impact to, of course, to the calculus of variations, quasi-conformal maps, non-Newtonian fluids. Indeed, Ladijinskaya, Nečas, Malek, Ruzhinska, Rokita, Bulishev gave important contribution to the theory of this fluid that present, in a sense, an alternative model to the Navier-Stokes one, because everything started from this idea of Ladijinskaya that suggested to replace in the Navier-Stokes equation the Laplacian with a non-degenerate P Laplacian, okay, with P sufficiently large in order to beat the criticality of the system and earn coercivity, and therefore solving the problem. Now there were uncountable developments. For sure, I missed lots of things, but we can recall the parabolic theory by Di Benedetto with all the intrinsic geometry theory, problems related to quasi-conformal maps with the contribution of Ivanek, then fine regularity properties of solutions and nonlinear potential theory by Kirpenainen and Mali, contribution of John Lewis, of Manfredi, and eventually Mingione with the nonlinear potential theory and nonlinear causal theory. So this is just to say how diverse can be the theory of P Laplacian and how developed, how advanced it is now right now. Indeed, Manfredi, let me mention a few that can be useful also at later stages. This talk, Manfredi indeed obtained the very first complete Schauder theory for P Laplace equations. Indeed, those are beautiful results because their statement is very simple. Okay, this P Laplacian plus elder ingredients, solutions are C1. That's it. Dramatically simple, but sometimes very involved for the proof. Let me in particular highlight that another crucial aspect of non-homogeneous PDEs when ingredients and in particular non-homogeneity appears is to understand the relation data solutions for this class of problems. Now, it is very well known that for linear equations, think about the Laplacian, okay, representation formula are available. This means that you have a right-hand side, you can represent, you have an explicit expression of your solutions that comes by the convolution of your the right-hand side term with super singular term. Okay, you have representation formula, so you can transfer immediately all the smoothness information coming from the right-hand side and translate them at corresponding regularity information on solutions. Okay, and this is several important crucial consequences. Problem: representation formula is no longer available for nonlinear quadratic PDEs and a fortiori for PDEs of the P Laplacian. However, employing nonlinear potentials, it is possible to recover a ghost of the representation formula that in any case allows you to prove pointwise potential estimates. This is the zero order type due to very influential paper of Cristiana and Marie, that gives you the best possible relation between data and solution. What you can do is connecting in the best possible way all the integrability, oscillation properties, size properties of mu, and transfer them in an optimal fashion on U, because this is listed apart, okay, except from a localization term. This is precisely the same role as the same effect that a representation formula would have. Now, what is really important here, this is what happens at the zero order level. So using potentials that encode the same scaling feature of the operator. Now, what is really surprising is what happens at the gradient level. This was, okay, one moment, stop formally. This was, I mean, among the finest mathematicians studying this mathematics. So it's, and this picture was taken outside here, right, Rosario?
Yeah. Then it's be on the left.
Doesn't matter.
It should be on the left.
Okay. What is really surprising is what happens at the level of the gradient. It was thought for a long time that these potential bounds were false at the gradient level. They're actually not only they are true in the scalar setting and in the vectorial one. But here you can see the very same effect that the representation formula of the Laplacian would have. Okay, so here there is I1 is potential. So what you can see is a total linearization effect that reduces the P Laplace equation to the Laplace one up to the C1 level. Okay, so these pointwise gradient bounds allow to not only to perfectly transfer any kind of information you have on the right-hand side term to at the gradient level, but above all tells you that up to the C1 level you have essentially similar behaviors, analogous behaviors for the general quasi-linear equations and the Laplacian one. Okay, now I'm talking about regularity for functionals and equations, but of course this is the basics for lots of very rich theory, very rich and far-reaching theories, where regularity theory is a crucial fundamental ingredient. And just thanks to obstacle problems, free boundary problems, fully nonlinear equations, Monge-Ampère, integral differential equations, homogenization, optimal transport. In all these fields, regularity theory is a cornerstone. You can do it without it. Now, what is said so far, historically speaking, was initiated, of course, on scalar equations. You know, you start from relatively simple problem, and then you rest less. What happens to systems or to vector valued minimizers of variation element? One can think, okay, we already saw that in the vector valued case, Uhlenbeck result tells us that p-harmonic maps have locally the continuous gradient. Let me mention that this is sharp, thanks to counterexample you got already in the class. Careful. We saw that p-harmonic maps are minimizers of the P-Dirichlet energy. Beautiful functional, depending on the modulus of the gradient. This essentially kills all the possible contribution that might come from different directions in the vectorial setting. And even not knowing this, back in the days when the George theory was established, the rumor was that, okay, a couple of months and also the vectorial setting will follow, we have a complete answer to the Hilbert problem, both in the scalar and in the vectorial. After 2 weeks, a 2-page manuscript by the George came out saying that, okay, this is not really the case. Indeed, one can produce a counterexample. One can construct an elliptic with discontinuous solutions. Of course, here coefficient must be taken discontinuous. Otherwise, the Georgian theory would kick in and would give Elder continuous solutions. So this is not the case, and this is actually a simultaneous contribution by the George and by Mazia. Mazia constructed the higher order elliptic equations with discontinuous solutions that can be nonetheless recast in the form of a system. Okay, so there are those two first counterexamples that immediately break down any possible hope of vectorial regularity. And in general, when a singularity comes, it doesn't come alone. It can come in, let's say, in battalions, if one wants to recall Shakespeare. Indeed, this is a profound result by Yeoman and Sarah, dating back to the 89, that tells you that it is possible to construct an elliptic system of this form, again with the elliptic coefficient matrix, with solutions, energy solutions that are discontinuous on a dense set. So discontinuities may be a lot. But, however, the very final answer to the failure of Hilbert problem in the vectorial setting is due to Nečas, because somebody could say, okay, all these counterexamples that you showed me so far have all these continuous coefficients, so maybe singularities are not an intrinsic phenomena due to the vectorial situation, okay? But comes from the fact that you consider a bad coefficient. Come on. No, this is false. Indeed, Nečas was the first one to construct an integral functional as prescribed by Hilbert. Okay, so perfectly smooth, perfectly regular, featuring a W12 minimizer whose gradient is discontinuous. So counterexample holding for energy multi-integrand and whatnot, strongly elliptic, strongly convex, whatever you want, with whose gradient is discontinuous. So counterexample that told the gradient Nečas. And this counterexample was pushed further by Zverak and Jan, who constructed the examples, who essentially proved the occurrence of singularities at all possible states. Constructed variational integrals again of the type prescribed by Nečas, with featuring either unbounded minimizers or non-Lipschitz minimizers. Okay, so this should, in some sense, convince that point-wise regularity in the vectorial setting is false. However, what could, let's say, be more subtle, if you want, dig further and say, okay, what can be said in the vectorial setting? Can I say that if I really don't care about point singularities, I can at least a reasonably large set on which things, in which I record essentially the results holding in the scalar case, and then another set in which bad things might happen. Well, this is of Justin, Miranda, and Murray that tells you that if you take energy solutions to this system with strong elliptic coefficient and where A is uniformly continuous, then you can find an open set on which solutions are Elder continuous, an open set of full dimensional Lebesgue measure on which indeed solutions are Elder continuous, and whose complementary, that is negligible, has also dimension less than n-2, and it is called the singular set, precisely the set on which bad things might happen, and Aside from that, it is very small, essentially negligible with respect to Lebesgue measure. Everything is okay. And also integrants of the P-Laplacian type with other coefficient, and essentially same result can be recovered. Pushing also for gradient regularity, one can find again an open subset of full and dimensional Lebesgue measure on which gradient is at the continuous. So the result for who is not seen by the n-dimensional Lebesgue measure, on which things might be big. Okay. This sort of results actually hold for more general class of variational integrals that are not necessarily convex. Indeed, let's say that in that convexity in the vectorial setting is quasi-convexity, meaning that you're essentially prescribing a sort of integral form of justice inequality. Okay, and what happens is that quasi-convexity turns out to be necessary continuity, and therefore it is crucial. So after enforcing a bit the notion of quasi-convexity, because as it was prescribed by Murray, it was rather too weak to derive reasonable regularity results, even almost everywhere, so it was not enough. However, enforcing the quasi-convexity condition, is it possible to extend partial regularity results also to quasi-convex variational integrals, whose proof is still the cornerstone of several other of various extensions and various other quasi-convexity other partial regularity results in the quasi-convex setting. Okay, so in a nutshell, what can be proved for quasi-convex variational integrals? Again, you can find an open set of full and dimensional Lebesgue measure on which minimizer have locally and the continuous gradient. The complementary of this set is negligible with respect to the Lebesgue. In this case, concerns the Hausdorff dimension of the singular set. It is really smaller than the ambient space dimension. Other question: is it possible to get explicit bounds on the Hausdorff dimension? This was a substantial open problem raised by Giaquinta at the ECM in '87. Okay, I'm bad with it, but still, it was an important problem. Now, a first answer to this problem that is providing explicit bounds on the Hausdorff dimension of the singular set was provided by Christensen and Mingione for both concerning strongly convex variational integrals with non-differentiable ingredients, as well as quasi-convex functions. Indeed, what happens is that you prescribe the usual ellipticity of the P-Laplacian type, even though the generic is fine. Non-differentiability in the ingredients, you do not need to be able to differentiate, because I mean this is the classical setting. And then it is possible to derive a computable number that depends only on the data of the problem, such that partial regularity of course holds, and the Hausdorff dimension of the singular set is quantitatively below n, below the ambient space dimension. Okay. And the same, very surprising indeed. I mean, quasi-convexity is very known. Is the some sense. Okay, now I'm talking against my interest. No, I'm joking. They are very non-local, and this non-locality is a substantial disruption to regularity. Substantial, in the sense that there are no ways, at least so far known, of quantifying oscillations. Okay. But what was proven by Christensen and Migione is that if you consider quasi-convex variational integral with the, of course, strict W1 strict quasi-convexity, because it is what it is, that is necessary, then one can find, and you consider careful, Lipschitz continuous minimizers, everywhere Lipschitz continuous minimizers, then you have a dimension reduction of for the singular set dimension. Okay, careful. This W1 infinity assumption is maybe either a class of model studied by Chipotanes, for instance, and Raymond. What can be seen is that if your variation, if your integrand at infinity behaves as the Laplacian, one can prove Lipschitz continuity. So all the class of model is covered. Okay. Now, concerning bounds on singular set, there are several other GMT pre-discontinuity problem. So it is I mean, it's again an ubiquitous problem, the one of bounding the absolute dimension of the set where singularity is bound. Okay, because it is natural that you want to know if things go bad, in quantity, how bad things can go. Can I quantify how big is the set where my minimizers behaves wildly? Makes sense. Okay, now let me turn back to non-uniform ellipticity. Okay, here, of course, we specialize to functionals, because whenever you're dealing with non-uniform elliptic problems, if you want to preserve as a starting point the full energetic information, you want to consider variation of the term. Otherwise, some information might get lost if you just stick to equations. Okay. But still, the catch between variational integrals and equations, of course, is the Euler-Lagrange that talks by minimality. Okay, now let me recall that uniform ellipticity means already in the most simple linear case, means that the ratio between highest eigenvalue and lowest eigenvalue of the ellipticity matrix stays uniformly. We are talking about, we want to bring this notion into the nonlinear setting, at least on a formal level. We differentiate the equation, do as we did before, rewrite it as a linear equation in a depending on the gradient, and then essentially recover. Essentially recover the full motion. More precisely, one can use two in order to measure the ellipticity of your matrix, and it is a function. So of course, you are looking at the lowest and the highest eigenvalue of the Hessian of F. And again, you can formulate uniform ellipticity whenever the ratio between P2 and P1 is uniformly bounded. If this is unbounded on at least one value of that, you're talking about non-uniform ellipticity. Okay? And this is a rather crucial concept that is strongly related to gradient regularity. Okay. And the matter of non-uniform ellipticity has been intensively studied before the 70s by real stars of mathematics, like Duraltsevan, Gilbert, Stampake, and but also after the 80s, Zhikov and Marcellini that gave impulse to what is the modern theory now. Indeed, Zhikov is concerning the sharpness of the facts, and Marcellini that set the foundation of the modern variational approach to to this class of problems. Indeed, before, let's say, the main tools that were used were either barriers or global methods, or the existence of strong solutions, work with the W1 infinity solution, so killing a priori the non-uniformity of the equation. Okay, and now Marcellini introduced a modern variational approach that, for start with, at least for autonomous problems, a regularity answer, complete regularity answer in the genuine energetic setting that is a W1P or W1 work. Okay, now in the literature, the most common form of non-uniform ellipticity is the polynomial one of the gradient variable, and indeed an effective way to formulate the lowest and the highest eigenvalue of the echelon of F are proportional to two different powers of the you not only are quantity of your integral, but you are also. This is crucial because it turns out that from counterexamples to Marcellini and Giaquinta, that a condition of this form is both necessary and sufficient for regularity. If certain thresholds are violated, then severe irregularity phenomenon might happen. In particular, for autonomous problems, the only sharp result known concern boundedness of minima. Indeed, the counterexamples were found out by Marcellini in 1991. The positive result, the regularity result, was eventually obtained by in 2021. So this is for this regularity theory with a gap of 10 to 30 years between one and the other. Okay. Now, it is natural to wonder what happens if I plug in coefficients. Are there new phenomena? Can I expect regularity? To what extent can I expect regularity? If I plug in ingredients, so I consider non-uniform elliptic integrands with other coefficients, for instance. Well, one let's say very simplified model, but as I will show you now, in fact, what is the expectation for this class of functionals is the double phase integral that was introduced by Zhikov in the setting of homogenization and for studying possible occurrence of Lavrentiev phenomena. Now, this is a rather simple model, right? It is just the sum of P energy plus non-negative weight Q energy, okay? And what is the problem? Well, the problem is that A is allowed to vanish. So in principle, this is pointwise uniformly elliptic, but the coefficient doesn't have enough to rebalance oscillations around the point. Very much the amount of non-uniformity displayed by this. Okay. Indeed, as I was saying, the pointwise ellipticity ratio is uniformly bounded. However, let's say coefficient might behave by it.
Roger is
Indeed, let's say the responsible of the non-uniformity for this functional is precisely the coefficient that sometimes vanishes, that might vanish in an uncontrollable way. This study was started by Jikov with a series crucial esposito Leonetti in Mingione, Fonseca Male in Mingione. What they prove that threshold is violated, then monsters may appear. In the sense that you can construct defined on balls, if you like, on Lipschitz domains, smooth domains, whatever you want, that hold in the scalar setting for radial functions, depending on the modulus of the gradient. A is either continuous or even more, but what happens is that minimizers have a singular set of essential discontinuity points do not belong to W1 P plus epsilon for all epsilon. And this is a genuinely non-uniformly elliptic phenomenon. Indeed, singularities, the formation of singularity doesn't come from the boundary, because the boundary is a cube, a ball, whatever you want, doesn't come from the boundary datum that is smooth. So it is only generated by pathological interaction as a coefficient and gradient variable. And in these counterexamples, this condition plays a crucial role, and keep it in mind as it will turn back. But let me insist more on this, and that is nowadays the state of the art. I studied them and I also use them to study about Lars Dilling and Miguel Sternashoff, which proved that I mean they got to the top level in the sense they constructed minimizers of double phase problems, again with smooth boundary datum, smooth domain, with maximal possible out of dimension of the singular set of the set of non-level points. Now you cannot go better. You cannot go beyond W1P. Okay. Also, if you have logs, also if you plug in logs, things might go wrong also for logs beyond W1P. So this is the best possible counterexamples you can construct, and in particular, they hold in the full energetic setting. Those are minimizers, and this is very important. And in particular, this highlights the complete failure of Schauder theory. Indeed, the validity of Schauder theory for uniformly elliptic operators, such as for good P take the Laplacian, is a classical fact nowadays, and one can wonder what happens if I see in innocent other coefficient. Okay, can I say something? Well, this is, for instance, a comment of Lieberman under in the math review of the paper by Giaquinta and Lucien Krell, that says that okay, all your perturbative techniques perfectly works in the uniformly elliptic setting, but dramatically face in the non-uniformly elliptic ones, unless you start with W1 infinity solutions. That is a bit like cheating. Indeed, this is the obtained Schroeder theory in non-uniformly elliptic problems, but look, all the ingredients of your so you have to differentiate your equation with respect to all the entries. You are taking and then for the gradient. Let me highlight, this is a comment to this theorem, a comment due to Ivanov. Ivanov said that the real obstruction here is the impossibility of proving uniform gradient bounds for probably approximating problems. But the lack to prove, for instance, gradient elder continuity. And this is, I mean, Ivanov identified what was the crucial obstruction to regularity, the lack of uniform gradient bounds. And the same is highlighted by whenever you have a non-uniformly elliptic equations, the very first and crucial step you need to make is proving gradient boundedness. Once you have achieved that, then you can prove higher regularity by more standard techniques. Okay, and an answer to those two problems was eventually obtained by Minjon and myself in those two papers. And what I would like to stress is that, first of all, the crucial point, yes, Ivanov was right, is proving gradient boundedness. And our approach is the first one, to the best of my knowledge, since the 20s of the previous century, is that for the first time, we do not pass through elder continuity for retaining gradient boundedness. How the way it was done before was, okay, I prove that the gradient is elder continuous out of the time exponent, then I retain boundedness, okay? And then if my operator allows, I push the continuity up what I can, okay? Here, elder estimates for this class of problem works in a terrible way. I mean, no, simply do not work. So what we do is a direct proof of gradient boundedness. Moreover, for this class for non-uniform elliptic problems, you can switch from starting from W1 infinity solutions to W1P. I mean, if the ellipticity of your variational integrals pushing W. Okay. And I will just conclude with the model result that will let me consider this variational integral where f is PQ non-uniformly elliptic, so this is the degree of, we get the optimal bound of already seen in the double-faced case. Okay? So this is the bound that works for pointwise uniformly elliptic problems. Then, under this condition, we can prove that the gradient is locally elder continuous in omega. In case we are dealing with non-singular or non-degenerate problems, we can do even better. This is classical Schroeder theory. Okay, what we can prove is that whenever my integrand is non-singular or non-degenerate, then we recover the full Schroeder implication. That is, A is C0 alpha, U is correspondingly C1 alpha, of course, for alpha less than 1. Okay, and so this is the last result that I wanted to show you, and many thanks for the attention.